Alright, here's 8.3. Our schedule only says 1 day, but video-wise, just because it's a lot, I'm going to break it up into 2. This first day is just going to introduce means. I'm not going to do any 4 steps. The notes actually have 2. But again, we'll wait till the second day because there's really 2 things I want to accomplish in this lesson, which is to, 1, introduce the t distribution, or a t interval, and then to show you how, there's a big discussion to be had about what's different about that and why we have to do it. And then with a t interval, we have to do a little work to get our critical value. We can't just do the 1.96, 1.645, and 2.576. Like the 3 critical values that we memorized for proportions we can't use. Now you see here, at first glance, it kind of looks like we do. And on one hand, we theoretically could just stick with all the z procedures like we did with proportions. Right? Down here for the definition, we see p hat just becomes x bar. There's your z critical value. And then your standard error formula changes because this is a mean and not a proportion. And that's about it. Okay? In fact, I'm going to do a margin for error problem, okay, just to kind of get that out of the way, because we could see those too. And I also want to get some context out there to kind of illustrate why this setup would potentially pose some issues for us. But the setup is the same as it was with proportions. It's just the standard error component is different. So here's a margin of error problem. I want 95% confidence, so I'll go 1.96. Sigma is 50. We'll throw that over square root n. And we want to be within the margin of error of 2 points. Right? This is measuring the average improvement from taking the SAT from the first time to the second. Okay? Remember that first line that we have where everything is plugged in? That would be considered your supporting work. Okay? So in your notes here, when I'm showing you all the steps, you don't have to show every one, but I want to make sure that you know what to do so you can get the second part of the problem, which is, citing what the desired sample size is. Next step would be to multiply both sides by the square root of n. Then I would divide by whatever 2 over 1.96 is, obviously some number that's a little bigger than 1. And then to finish it off, I'll square it. Obviously this big mess on the left side is just going to a calculator. And this one comes out to be a whole number. The other one we didn't. But 2,401 would be our desired sample size. Okay? You should have an example in section 2 that looks just about the same, except it had a different standard error formula and a different margin of error because it was for a proportion. Now, I wanted to work in this problem just for the context to talk about why we're making this next step to using a different distribution. And the issue is right here. To take this approach and use the standard normal curve to determine a margin of error or construct an interval basically demands that we know sigma. Okay, sigma is a parameter. It's the standard deviation for our population. it's not very likely that you know sigma. In fact, I think the first slide had a little note at the bottom that says we don't use this very often. That was the Z setup, because we typically don't know sigma. And the reality is, if we don't, we can't use it. It's part of the structure of a confidence interval that we have to. We've got to have other options, and that is what leads us to this. When sigma is unknown, we go to what's called a t-distribution. Okay? The solution that we come up with is actually relatively simple. Okay, in terms of just understanding like how we combat this issue, right? Again, if you know sigma, you could use the z. Okay, down here, notice the only thing that changes is sigma became s. Okay, now notice down here, S is the standard deviation of the sample that we took. Okay? That's not sigma, but if we sampled well and sampled randomly, S should be pretty close to sigma. Okay? Now, it may not be the exact same, so we can't use, the Z distribution anymore, but this is where the T comes from. Okay, notice that from here to here, one adjustment was made. Sigma's out, S is in. Okay? Because we're saying we don't know sigma, using the Z distribution is out. So we go to the T. Okay? So the next step for us here is to learn a little bit about what the heck the T distribution is. There's really two characteristics that you should absolutely know, right? This is comparing some data. You have a Z at the bottom and a T up at the top. It's still symmetric. It still has a single peak. It's still centered at 0. But here's what you're going to find. Two characteristics that you should know. Number one, this is specifically compared to the Z. It has a lower peak, which basically means it doesn't have as many outcomes around the center. Okay? The fact that we're using an approximation for S means that we're just going to have more variability. You can also see it right here compared to the distribution below. It has wider tails. And again, if you just think about this on a really, really basic level, it kind of makes sense. Right? We don't have sigma, so we used an approximation. So from one sample to another, right, this is going to measure repeated samples, we're going to have more variability, okay, in building our interval. One, because we're approximating mu, that's the whole point of all this, is to approximate a population mean. And to do it, we're using an approximation for sigma. So we've kind of got variability coming from two different places. That's not like exactly what's going on. That's a good way for you to think about it, because that's more or less what's happening. This deal down at the bottom, the degrees of freedom, we'll get to on the next slide here. What degrees of freedom basically says is the exact t distribution that you're working with varies. Depends on how big your sample size was, because degrees of freedom is n minus 1, which might seem a little bit odd, like why don't we just go off of the sample size? There's a lot more to degrees of freedom. So degrees of freedom isn't always just sample size minus 1. We'll see that a lot the rest of the year, but just kind of go with it for now that it's sample size minus 1. Basically what's happening with degrees of freedom is this, okay? And here's how I want you to think about it. You have three curves on here. The dashed one is 2 degrees of freedom. So that would mean that's a t distribution that was the result of taking a sample of 3. 9 degrees of freedom would come from sample size 10, and standard normal, the purple one, is the actual z distribution. as your degrees of freedom go up, the t starts to basically turn into the z. It gets closer and closer to looking like the z. Okay, so you'll see two things happen on this diagram. The peak's getting lower, and the tails, back up. The peak is getting higher, and the tails are losing their area. Okay, and here's how I'd want you to think about this. Okay, as n increases, S, theoretically, if we meet the random condition and we're taking a good sample, should be getting closer and closer to sigma, which would mean the t distribution that we're working with should look more and more like the z. It's kind of a domino effect. Sample size goes up, our approximation for S should be getting really good, and it's probably quite close to what sigma actually is. So then the specific t distribution that we'd work with is going to be closer to the z. All right, this is table B. It's in your packet. Okay, but because the specific t distribution that we're working with depends on the degrees of freedom and how big our sample was, we can't just have a one-size-fits-all critical value. It doesn't work like that. It depends on our degrees of freedom. So here, if we're going 90%, I go down at the bottom, and I see right here, 90% confidence level, sample size 10 would have 9 degrees of freedom. Okay, so notice down here at the bottom, 1.645 is like the critical value if we could use a z-score to do it, but we can't, right? Because we're approximating sigma from a sample size of 10. But that's kind of like the critical value that we would like to use, but we're going to have to use one that's a little bigger. And then in the table you can see right here, we'd have to use 1.833. So if we had sample size 10, we have 9 degrees of freedom, and then that's the critical value that we would use. Let's do another one. If you were to go off the table, right? I'm not getting into the calculator stuff, but in day 2 we'll do some 4 steps, and that's when we'll get into the calculator features. But if you had 99% confidence, okay, notice down at the bottom here, we'd love to use 2.576. We can't, right? And again, the reason we can't is we don't have sigma. Okay? We approximated sigma from a sample of 58. So notice that in table B, these critical values, as your sample gets bigger and bigger, right? If you just focus on this particular column, these critical values get closer to 2.576, right? That's because our approximation for sigma is getting better and better and better. Okay? What I want you to see here is there is no degrees of freedom for 57, so we just simply round down. We use 50, and we'd have 2.678. All right, we're basically to the point where in day 2 what I'm going to pick up with is just to review the conditions and then dive into some 4 steps. But now the structure for an interval is going to look like this, right? You have your statistic. We call that x bar. That didn't really change, right? You're going to get x bar from taking a sample. This is different, and that's a little different, right? Notice my standard error formula doesn't have sigma. We're going with S, and that's typically going to be the case. So we have to adjust our critical value a little bit and use a t procedure instead of a z. Okay, both 4 steps that I'll do in day 2 use the t procedure.